Hello! Right, last chapter. This one is on spectra, okay, which is the plural of spectrum. Okay, if you would like to have a little read about the history of all these things, page 223, you'll have a little read about that and you'll see where physics ended up as a result of the first investigations on spectra. So have a little read of that if you like. Press pause. Okay, so turn to page 2, well, you're on 224 now, so line spectra. This is something that tells us a lot. Obviously, light carries information. It's a wave, it carries information. And if you can use that information somehow, then that obviously will enhance your understanding. So the idea is that hot objects tend to give out different wavelengths, okay? It's what's called a continuous spectrum. So anything that might, say, be quite hot might give out lots of different wavelengths, and if you look at the across the visible spectrum, those wavelengths correspond to colours. So you can have a little look here, okay? There's two types of emission spectra. Okay, so these things here, so this is a continual emission spectrum, and all different wavelengths are being emitted by whatever this object is, from violet all the way up to red. Okay, so the longer wavelengths. But then there's other elements, or particular elements. Let's say you've got a hot gas containing just one type of element perhaps. Instead of coming out in all the colours of the wavelengths, you get very definite single wavelength lines. Okay, so these wavelengths must correspond to something, but they are a definite value. Something is happening in that material to make only definite frequencies, exact wavelengths, be emitted by something. So that's called an emission spectra. And again, the reasons why this occurred obviously help lead to their understanding of what goes on inside the atom. Okay, there's another type of spectrum, but instead of being striped lines that are being emitted, okay, across, let's say something that's giving out all the colours of the spectrum, if there's something around the outside that can absorb definite wavelengths, exact wavelengths, then where they're missing, you see a black line, the absence of light. Okay, so that is what you call an absorption spectrum. Okay, so that might be, say, something hot has got a cold gas around the outside or a cooler gas around the outside, and they absorb certain wavelengths. Okay, so you've got absorption and emission spectra, but again, you've got these lines were the things that had to be explained quite clearly, okay? So, the origin of that was explained a little bit by talking about, again, electrons and discrete energy levels, exact frequencies, exact wavelengths, which correspond to how we draw the energy levels in atoms. So if you have a little look on page 226, okay, you'll see the couple of equations that we do need to use, again, like we did in the last topic. Okay, so these equations, so the energy equation for a photon with a certain frequency, and again, if you want to put that in terms of wavelength, that's quite useful here as well. So the idea that you can actually draw these little energy level diagrams, which look something like this, okay? So you have, and again, it'll say not to scale, but basically this energy is a negative number because you've got to put that energy in to get it up to 0. So electrons can occupy these energy levels. And the lowest level is called the ground state, which you may have heard. And all of these levels, which are excited states. So there's a bit of extra energy, they can go to a higher energy level. But the idea is that any time, let's say you've got an electron that's quite high up and excited, it's got a bit of extra energy to get there. When it goes back down again, a photon is emitted. Okay, and the difference in energy between these two levels will tell you the frequency using the Planck equation, E equals hf, or you can find the wavelength from that too. So the idea is this exact transition that can happen inside an atom, so from being excited to going back down to the ground state, that will give out a certain wavelength of photon. Okay, and it's the other way around. Let's say you start off on the ground state or low down. Okay, you might then say, okay, I'll absorb a certain amount of energy and I can get up to a level. So that absorbs photons. So we've got a mechanism where it talks about absorption, going to a higher energy level, and this one, emission, going to a lower energy level. Okay, if you don't quite get enough energy, you can't stop halfway up. It's got to be all or nothing. And if you go beyond, you're still going to sit on that level. You haven't got enough energy to get to the next. So it's absolute definite. There's no in-betweens, okay? It's not like shoes. There are no half sizes. But there aren't anymore, are there? I don't know. Anyway, so that's about it, okay? So if you want to know how much energy is going to come out, okay, you look at the energy difference, and if it's going up, that's the energy it absorbs. If it's going down, that's the energy it emits, okay? So it's the difference in two energy levels, like that. So the difference in two energy levels is equal to hf, or in terms of wavelength, it looks like that. So find the difference between the two levels, and that'll tell you the frequency and the wavelength of what's come out, okay? And that will be essentially the photon energy in joules, okay? So it's all quite a useful little thing, okay? It's always done in electron volts, so you will need to remember the conversion from electron volts. But if you have a little look, there's an example talking about that on page 227, and then there's some questions you can have a go at yourself Okay, so why don't you have a go at the questions on 227 and 228? Press pause. I'm ill. Right, okay, so that is quite straightforward to understand, I hope, but that's the idea, okay? So the idea is that it's only really simplistic cases we talk about. Obviously, some spectra, you'll get emission spectra and absorption spectra where there's loads of different atoms, and in that case the spectra gets really complicated, but again the pattern, the spacing, the wavelengths are characteristic for each element. So this process is brilliant. You can look at a star billions of light years away, look at the spectra of it billions of light years away, galaxies that is, isn't it? Okay, fair enough, but you could in theory again from galaxies see what elements are actually inside those galaxies, okay, or nearby stars. Again, look at spectroscopy and you can identify what elements are in there, and that is a very useful technique. Alright, so if you want to have a little look, that topic isn't very long, so the summary is there on page 229, okay, so have a little look at that. Basic ideas about electrons being promoted or relegated, depending on what words you prefer to use, okay, to different energy levels. So just read the summary, and then again there's some exam questions on 229 and 230. So have a go at the exam questions, check your answers, and if you're not sure about anything, come and ask. And again, have a go at some past exam questions, okay? And make sure you're confident with these things before you go anywhere near the exam, okay? Good luck and enjoy yourself. So.